Hello, everyone. I hope you are hearing me well at the back. Give a sign. OK. I hope you are also enjoying the conference so far. I would like to thank you for being here. This will be a personal story how I try to onboard a couple of functional programming languages when it comes to serverless computing, how the landscape looks like right now. And it will be in the form of a story of personal experience with some evidences. I did some measurements, test scenarios. I can give some tips. I made the talk as much beginner-friendly as possible, so if you don't know anything about serverless, you are also good here. A little bit about me. Sorry for technical problems. Yeah, so for those of you who don't know me or didn't read the conference page, my name is Wojciech. I'm also available under nickname Gawroński over internet. I'm a software and operations engineer in Appliscale. We are a small consulting company focused on real-time bidding systems, real-time scaling, cloud computing, and so on. I'm majorly responsible for writing code in Erlang and Elixir, but also doing DevOps and working with AWS Cloud as well. Obviously, there must be a shameless plug. At the bottom of the slide, you can see that we are hiring. If you are interested in such topics, let's have a talk afterwards. I would love to answer your questions. I would like to start with providing common ground for everyone and discussing what is serverless in the first place. And I will start with a little bit of ranting, because as the IT industry, I think we suck at naming. There's a very famous joke about there are two hard problems in computer science: cache invalidation, naming things, and off-by-one errors. So basically, with serverless, it also looks like this, like the picture you can see here. It's a noisy, overhyped word. At the moment, it simplifies the reality, and many things are actually confused what it really means. So probably nothing unclear for you, but at the end, we have servers down there. We need servers. We need hardware to execute our code. That's obvious. We also need operational people. Someone has to monitor, manage that infrastructure, configure those services for us. And I think that the better description, the serverless buzzword, is when we look into the brief history of cloud computing. And that's natural evolution, basically. So we started with renting hardware and constructing our own data centers. Then we moved into the more consuming way of for the infrastructure when it comes to infrastructure as a service. Then we've got platform as a service. And then finally serverless, which is the, let's hope it, ultimate way of executing programs on someone else's infrastructure. Basically, it's a transition from owning to consuming. And serverless is hopefully the last step as well. In the current landscape, we can distinguish two flavors of serverless computing. One is called backend as a service, and if you use Parse or Firebase, you basically used that particular flavor. Also, there's very important second branch of that serverless computing thing called function as a service. And it's basically a way of running our code on demand on someone else's infrastructure and do not worry about operational hassle related with it. And the first word from that acronym suggests that we as a functional programmers are in a privileged situation, because we means that we can think in a unit of execution, which is a function, which is natural thing for us. And is that true? Is that really true? We will address that in the presentation, and that's also my concern that it's not exactly that way. I think that there is plenty space for optimization and doing stuff better. Let's start with also describing how the serverless work and how it affects the pricing model, because that's very interesting for us. So at the beginning, we are preparing source code and bundling it into a package. It is either zip file or jar file. And that particular package, combined with the configuration, in that sense, I mean, the amount of settings that we need to provide to the provider about, for example, how much RAM we would like to allocate, package and the configuration together are uploaded to the service. And from that particular step, we are basically off. Everything else is handled by the provider. So it means that scaling, infrastructure, and operational hassle is done on their side. It means also that we are giving up control, because in exchange for receiving such nice capabilities like do not worry about operations, we are basically skipping that particular bit about choosing the operating system or choosing the hardware on which we will run. That it is either a benefit or a problem for us, depending on the context. And that also affects the pricing model, as I said. So I hope that is visible on the diagram, that we allocated and created an execution unit that consumes half gig of RAM. If our build time, if our real time is basically 120 milliseconds, we will be rounded up to the bucket of 100 milliseconds, and that 200 milliseconds is basically our build time. So we'll be built by the execution time and the amount of RAM that we allocated for that Lambda. Additionally, we are paying for how many requests we are actually consuming with that Lambda as well. But that amount of requests is batched into very huge amounts, like million requests and so on. That's obviously being tricky when it comes to combining your Lambdas and executing them. But the major problem with cost effectiveness in that scenario is that we need to optimize for execution time as well, and also for memory footprint. So knowing how it works and what is it, let's talk about why we should bother with this approach. And I wanted to prepare a couple of slides here, but there is very, very fantastic paper prepared by Gojko Adzic and Robert Chatley about serverless computing and how it affects three areas: basically cost effectiveness, architecture, and operational factor. If someone would like to have this paper as a video or talk, there is a link also to the GoToConf from last year, performed by Gojko. It's a very nice talk. I recommend, if you are interested in the serverless computing, to watch it. I read that paper, I analyzed it, I prepared 3 quotes from each area that it covers, which basically provides enough information and builds up the context if you are interested in that topic. And cost effectiveness is basically an essential aspect of that paper, and it's even reflected in its structure. The most critical element in that paper is basically that table that compares serverless computing options in comparison to platform as a service or infrastructure as a service elements. And as you may see here, our reference price is basically Lambda with half gig, and everything else below is basically either platform as a service solution or infrastructure as a service solution, that it's much more expensive. What is also very important from the table is that Lambda includes failover costs when it comes to the other platform, other solutions. We do not. We need to pay it separately. So it means that by giving up some control over nitty-gritty details, we are also buying in something else, which is, in that sense, a failover operational costs and theoretically smaller amount of money that we need to pay for execution. Additional thing is related with architectural impact. So this is very extensively covered by this paper as well. And the most predominant one and the most important statement from it is that it allows better modularity for our programs. If you squint, this posted quote may look like a microservice architecture definition. So it's I know that it differs, but basically it is very similar to the premise that microservices architecture are giving. And wouldn't it be useful to have such elasticity and less operational burden? I would buy in. Last but not least, I would like to emphasize that it's not reflected in the title, but this topic screams from between the lines. Operational context and operational costs are very important for that paper as well. And there are such statements like this, supported by evidence and measurements, that are saying that for some cases they are basically saved 95% of their cost, operational cost, after moving to serverless. So that's very important as well. A key thing to remember is that applicability and context is the key. So if those definitions sound familiar for your use case, maybe serverless will be a good choice. I will show another example that choosing serverless will be a very bad choice. You may say that it's only one paper, and you are right. I would like to support it by real-world examples. Those companies are using serverless computing. It's very important to notice that use cases are pretty much different, and they are ranging from fully functional subscription-based MOOC platform or online collaborative mind mapping tool as well. Knowing what and why, I would like to talk a little bit about tech and finally go to the meat, so to the programming and functional languages. So at the beginning, when I started to getting interest into the serverless computing, I made a list of functional languages that are available in the landscape, and I focused only on languages that are forcing me to use a functional paradigm. I deliberately skipped languages that are multi-paradigm because I wanted to focus on those that are forcing me to do functional programming. I compiled the list, and I started to wonder which ones I can run on the Lambda, in that particular case on AWS. And I started to graph and look how many options do we have provided by the platform. And it looks like that in most cases they are sharing the same runtimes, like Node.js, .NET, JVM. But the key thing here is that we are basically limited from the start when it comes to languages that we can use on serverless. And that's a bummer, in my opinion. Another thing is that from those runtimes that are available here, only .NET is basically treating a functional paradigms and having optimizations implemented inside the virtual machine. JVM does not support tail call optimization yet. Node.js supports them, but in many cases causes the optimization. If you are, for example, using exceptions or something else, it will basically de-opt. And that's the V8 fault, not the Node.js itself. So it means that we've got limited choice and limited runtimes. But we can cheat. We can cheat a little bit. Additional thing that I have to mention is the shim approach, which is a little bit, as I said, cheating. It's a well-known workaround when you are able to run any executable that is compiled to the Linux infrastructure and then wrap it around with some small program written in Node.js or Python and redirect input-outputs in order to interact with it. Many people use that for using and dropping Go executables before they were supported. I used it in order to support Haskell, and that's the only exception that I did for platforms that are not directly supported during my tests. So limited by the runtimes and limited by the amount of cheating that I can use, I chose those languages to test and compare between. You may see that the Haskell, as I said, is the only exception from the rule that runtime is not supported directly, and I used shims for that. I choose also pure script, buckle script, closure script from the Node.js runtime, F# from .NET, and Scala and Closure from JVM. I have to drop all the Erlang and Elixir. I did that with aching heart, but I did the exception for Haskell. I dropped Elm because right now it's inherently a front-end language, It might change in the future. There is a movement into that, but it will be really hard to adopt other workflow. And I couldn't force the JVM runtimes to run Frege or ITA, unfortunately. I also skipped OCaml, but BuckleScript is basically proudly represents the family, I think. So I said a little bit about tested runtimes and languages that I choose. Let's go to the measurements and how I compared them. Each Lambda that I prepared, each implementation basically has two handlers, both accessible via HTTP endpoint. And I used post endpoints in order to cheat a little bit and avoid caching as much as I can. So I didn't use get in order to avoid caching on the API gateway level. First endpoint basically does no work at all. So basically it copies the request body and the content type to the response and basically echo everything. And the second handler is a naive implementation of an algorithm that gives us a primes number list to a given point. So I needed an endpoint that will, triggered with one argument, will do a different job and different complexity depending on the size of the argument. In both cases, Lambda does not perform any additional work, so it does not log anything and so on. I have 4 scenarios that I would like to test. I started with package size and compared them between the platforms. I then measured the memory usage and memory footprint, execution time, and those two are actually dependent on the input. And I measured the cold start time, which is very important when it comes to serverless, and we will talk about it. In scenarios 3 and 4, I used the prime numbers endpoint. For the 5th scenario, I used the echo. And when it comes to 4th point, I would like to emphasize that it's not a performance test, it's the cost effectiveness test. Because I measured the execution time, how long the Lambda runs, not how latent is the response, in order to infer how much we will pay for it when it comes to pricing. So let's start with the easiest example to compare. I hope that it will be legible for you. If not, bear with me, I will transcribe. So I would like to compare package sizes at the beginning before I will upload to the service. And that was pretty easy to get right, but there are some tricks as well with it. So you can see that bars marked with red color are basically JVM compliant platforms. Green ones are Node.js, and this one is .NET. This one is actually a Haskell footprint. Yeah, and basically, as you may see, JVM runtimes are the biggest one. Also, BuckleScript is pretty high because of the standard library and dependencies bundled with the package. For me, but that's the only my personal choice, F# is kind of a winner because it provides a very nice runtime and also has very small footprint when it comes to package size. One thing worth mentioning is that you need to know your tool chain. I attached here deliberately this huge bar, which is ClojureScript without optimizations. And that's not the fault of ClojureScript. What I would like to show you by that bar is if you will not enable enough aggressively optimizations, you will end up with bloated package. Because in ClojureScript, if you will disable all optimizations, you will basically bundle dead code and so on. So here's the real value for ClojureScript, and it's much smaller. If you don't know your toolchain or miss the optimization, you will basically have a bloated package. So far, so good. Let's analyze the memory footprint. This time, winner is not visible at the first sight. Green bars are basically Node.js runtimes, and they are, at the first sight, they are having the smallest footprint. Also, Haskell has pretty low footprint, which is this bar, call it a teal color. However, it is related with how we bundled the package and how we prepared the package. Because we use the GHC to produce the executable, which aggressively optimizes everything and drops off unnecessary stuff. It also means that without it, we basically, if something goes wrong with the executable, we are on our own. So that's a workaround and trade-off. I'm a little bit surprised by high position of ClojureScript, but maybe it's something related with the implementation. I would like to point out that Node.js-based runtimes are allocating the smallest amount of memory. However, pretty steadily, F# behaves also pretty steadily as well. So it's predictable, and we can also optimize for smaller lambdas, knowing that it will behave more predictably. This scenario is probably the most controversial measurement, so I would like to spend here a little bit. Once again, we do not measure here efficiency or performance. We are measuring cost effectiveness, so how long Lambda will run. And by that number, we will be able to know how much we will pay for it. For smaller numbers, nothing exciting is happening, but I skipped it deliberately because we pay for 100 milliseconds anyway. So if our Lambda runs 8 milliseconds, we are still paying for the 100 millisecond slides. Exciting stuff starts to happen with bigger inputs, and basically Scala and ClojureScript are consuming a lot of time, the execution. And they are significantly off. They are even hitting the hard limit at the end, which I choose 20 seconds. For me, clear winner is, again, the F#, because it basically it's steady and predictable. And knowing that, you can provide the most significant savings as well. Very important thing that I would like to mention here is that due to fire and forget nature of serverless, the containers are reused in a slightly unintuitive fashion. So if you would like to leverage JIT compilers or very fancy generational GCs, you are basically need to provide a steady workload in order to warm up those things. If your workload will be spiky and there will be no steady workload, after a certain amount of time, provider will actually tear down your container, and you will start with the cold start as well. And that is also related and perfectly described by Rich Hickey, who called those kind of programs by situated programs, and described it on his ClojureConch talk, which is linked. And for such programs that need to live for a long time, they are loading a lot of stuff into the memory, choosing serverless approach will be a great mistake. And yeah, last but not least, cold startup. In other words, how painful it will be for the end user to hit a cold infrastructure and then wait for container to warm up and load. And here, there are no surprises. The smaller runtime you have, the faster it will boot. So Node.js-based runtimes are winner here. As I said, the smaller runtime, it will load much faster. Another thing that I a little bit talked about on the previous slide was related with how AWS or how providers are actually recycling and reusing the containers. And there is a very great article about this. And unfortunately, that's the empirical study only. So there is no guarantee from the provider side that containers will live for that amount of time. Unfortunately, it's basically optimization on their side that they may handle or not. And from the empirical studies, it's looked like if your containers are idle for an hour, provider will basically tear them down. It means that, as I said, if you don't have steady workload, you need to either provide some health checks that will keep that instance not idling, or you will deal with cold start, and you have to incorporate that. Moreover, the biggest allocated execution units are tiered down a little bit faster. So it means that the more memory you will allocate for your execution unit, this 1 hour idle time will be much slower. So it's a sensible optimization on their side as well. And one thing that I need to stress out here is that every time we do a deployment or recreating our functions, we are basically dealing with this effect. So it means that if you are doing a deployment, you should warm up and then switch in order to have it properly warmed up, and do not affect your users by this cold start. And one additional thing that actually appeared during the test. So all concurrent requests that are hitting the cold serverless, your Lambdas, will basically pay the price. So it means that it's not about queuing, it's about all first requests that are concurrently hitting your infrastructure. So we talked about capabilities, we do measurements. I would like to talk about pain points and problems that are basically an opening to the discussion about how we can make things better. And I would like to emphasize again that it's always a trade-off. We gave up a control, and we basically received in exchange a less operational burden, but we need to apply additional rules and constraints to our code and solutions. So starting with the first thing, we do not know anything about containers and how they are reused and so on. And as I said, it might be a benefit or problem for us, depending on how close to the hardware we need to be. And we don't know anything about hardware, operating system, because knowing that it will be a Linux is like knowing that you are dealing with a reptile instead of animal. So it's basically still a problem and unknown. We don't know how it will be reused. We do have only empirical studies about that. Serverless is a pretty new approach, and that requires a set of new practices in order to do it well. And that includes debugging, observability, logging, and so on. Also monitoring and maintenance. And luckily, some work is done in that space, but there is definitely a lot of improvements that we can introduce here as well. Additional thing is about limits. So as I said, we gave up control. We need to deal with the constraints and limits. And there's plenty of them. So concurrency limits, space limits, disk access, package size, because we can upload at most 50 megs of jar file to the service. That's why I measured package size. Most of these solutions are advertised as infinitely scalable. And in practice, maybe they are, but you need to fulfilling their rules in order to achieve that. And the pressure points are put in a different place when it comes to designing such systems, in my opinion. So that's one thing that we need to consider. And choosing that approach, we are also at the mercy of the platform providers, that they will add a particular feature or support for that particular runtime. A canonical example would be AWS support for .NET Core. Up until January this year, they didn't support any version above 1.0. They didn't support even 1.1, which for people that are dealing with F# and .NET, you know what it means. You are basically on a very old compiler and so on. Another one, if you are choosing the thicker runtime, you will need to be prepared to optimize your VM configuration heavily in order to reduce the cold starts or fiddle with the garbage collection and so on. So that's additional knowledge you need to be aware of in order to do it properly. And again, last but not least, you need to know your tool chain. You need to know your tools in order to support it very well and optimize. And I fiddled with all those languages, and I use serverless framework for that. And in many places, I need to fight the build pipeline for the particular language in order to output some stuff in proper directories and so on and so on. A lot of yak shaving. It's not the hard stuff, but you need to do it. It means also that you need to do it on your own instead of rely on some plugins or additional tools. That's definitely a place that we can improve on. And the same remark can be applied to the optimizations, as I shown in the ClojureScript example. That's not a fault of ClojureScript, but you need to know which optimizations you need to apply in order to be thin and lean. So probably it's much information, so I will recap for you because we are coming to the end. The safest choice would be to use F# on Azure Functions or AWS. I'm not saying that you have to use it, but that will be the safest and sanest choice, the best support out of the box. And I'm not surprised at all because Azure is also a Microsoft stuff. If you have to use AWS, you are dealing with stuff that is introduced this year, a month ago, so there might be quirks. I didn't run into any, but there might be quirks when it comes to bigger implementations and so on. For me, a choice would be either F# or ClojureScript or something that is going on the Node.js runtime, but mostly F#. If you are seriously considering this approach, I strongly recommend to read that paper and watch that talk. Definitely worth time spending, enjoyable, and also very important information about context and about applications. And last but not least, again, applying those rules requires knowing everything about your use case. Without such attitude, you will basically apply maybe good ideas in the wrong environment, which will cause more harm than good. And that's all what I have. Thank you, folks, for being here. If you have any questions, I would love to address them. One side note, here are the list of the references, and at the bottom, you've got the repository link with all examples and implementations. Thank you very much.
Okay, so you mentioned some vendors like AWS and Azure, and do you have some experience or idea how to run the same packages on local machines or local servers, if you try to compare it to it?
That's a very good question. So there are a couple of alternatives. So for example, Serverless framework provides plugin called Serverless Offline. You are able to simulate that on your local machine. However, it won't work with every single example that I provided here. So for example, I couldn't force it to work properly with ClojureScript. Maybe there's an improvement that we can make. So not all tools are working out of the box with those examples as well. So yeah, there are tools for that. It's not like simulating 100% compliant infrastructure on your local machine, but you can do it locally as well. It's not a problem.
What are the names?
Serverless Offline, if you are using Serverless framework. And there is stuff called local stack, if I recall correctly, for AWS in particular. I don't know anything about Azure tools, maybe someone else knows.
So I was trying to see how Haskell did on your slides. As far as I could tell, it was often among the best, at any rate not far off. So could you say something about Haskell?
Yeah, so that's very right conclusion. Why I didn't emphasize on top of that is that you need to deal with the shim. So we're basically compiling an executable and then dealing with standard input and output, which might be a problem or advantage, depending on the context again. However, it went very well. So memory footprint was the best one, the lowest one. The same went with the execution as well. So if you are fine with having workaround in your system, that's totally fine and very, very good choice as well.
Hi there. Do you think that the application that you use to run Haskell can be employed to, I don't know, Erlang, for example?
Yeah, definitely. So you can use any executable. For example, people are using those shims to use ImageMagick tool for converting images as well. So you can use any executable that is compiled into the Linux infrastructure. The one thing that you need to consider is that you are compiling to a very general use case because you know that it's Linux and that's it. So there is no optimization for the hardware and so on. But that's things to consider.
Any more questions? Okay, so let's thank again our speaker for the presentation.